Hello viewers, in today's session we are going to discuss some important problems related to parametric differentiation, right? And we have already discussed the concept of parametric differentiation in our earlier videos. So here we'll solve some important problems. So the first problem is we are given two functions, that is x is equal to cos inverse of 1 over square root of 1 plus t square, and y is equal to sine inverse t over square root of 1 plus t square, where t is a parameter and here t belongs to the set of real numbers, right? So here we are given that x is a function of t and y is also a function of t, and we have to find dy over dx, that is the derivative of y with respect to x, and the second derivative of y with respect to x, right? So here t is a parameter and we have a function y is equal to f of x, where x depends on t and y also depends on t, and further y is a function of x. So let us see how we can find out dy over dx and the second derivative of y with respect to x. So now to get the value of dy over dx, what we do, we first find dx over dt and then dy over dt. So first we find the derivative of x with respect to t, then the derivative of y with respect to t, and then we find dy over dx by dividing dy over dt by dx over dt. So the first objective is to get the derivative of x and y with respect to t. So here x is equal to cos inverse 1 over square root of 1 plus t square. So we have to find dx over dt. Now see here we have a function of cosine inverse. So let us first simplify x and y by method of substitution or by introducing another parameter. So to simplify x and y, the most appropriate substitution is t is equal to tangent of say theta, right? So when we take t is equal to tangent theta, then we can simplify x and y, and then we can easily find out the derivative of x and y with respect to t. So when t is tan theta, then x is equal to cos inverse 1 over square root of 1 plus tan square theta. Now from trigonometry, we know that 1 plus tan square theta is equal to secant square theta. So 1 plus tan square theta is secant square theta. So this is cos inverse, and here this square root get cancelled with this 2 and we are left with secant theta. So now we have cos inverse, and 1 over secant theta is cos theta, and from inverse trigonometric functions we have cos inverse and cos, it get cancelled and we are left with theta, provided that the principal value branch of cos inverse, it belongs to the interval that is 0 to pi. So we have x is equal to theta, where theta is given by tan inverse of t. So now we have x is equal to tan inverse t. Now we can find out dx over dt by differentiating tan inverse t with respect to t. So the derivative of tan inverse t is 1 over 1 plus t square. So this is the standard result. So dx over dt is equal to 1 over 1 plus t square. So now similarly, we can simplify y. So y is sine inverse t over square root of 1 plus t square. So sine inverse is equal, this is tan theta for t, and here we have 1 plus tan square theta. So this is sine inverse, and we have tan theta, and square root of 1 plus tan square theta is equal to secant theta, as we have done in this case. So we have sine inverse, tan theta is sine theta over cos theta, and 1 over secant theta is cos theta. So cos theta and cos theta get cancelled. We have y is equal to sine inverse sine theta. Now again, from inverse trigonometric function, sine inverse and sine, it get cancelled, and we are left with theta. And provided the principal value branch of sine inverse is from minus pi by 2 to pi by 2, right? Okay. So here we have y is equal to theta, and theta is equal to tan inverse of t. Now dy over dt is equal to the derivative of tan inverse t, that is 1 over 1 plus t square, right? So we have obtained dx over dt as 1 over 1 plus t square, and dy over dt as 1 over 1 plus t square. So now dy over dx is equal to dy over dt divided by dx over dt. So dy over dt is 1 over 1 plus t square, and dx over dt is also 1 over 1 plus t square. So 1 over 1 plus t square and 1 over 1 plus t square get cancelled, and we are left with 1, right? So dy over dx is equal to 1, and we can see that the derivative of y with respect to x is a constant. So when we differentiate dy over dx to get the second derivative, that is d2y over dx2, then we have d by dx of 1, and the derivative of a constant is 0, right? So the second derivative, that is d2y over dx2, is equal to 0. So now consider this important problem. So here we are given a curve y is equal to f of x, which is defined by these two equations connecting x and t, and y and t. So here x is given as a function of t, y is also given as a function of t. So x is equal to 2t minus t square, and y is equal to 3t minus t cube. And we have to find dy over dx when t is equal to minus 2, and the second derivative of y with respect to x, that is d2y over dx2 at t is equal to minus 2, right? So let us first differentiate x with respect to t. So dx over dt is equal to d by dt of 2t minus t square. Now the derivative of t is 1, and the derivative of t square is 2t. So we have 2 minus 2t, that is 2, taking 2 as common, we have 1 minus t. Now similarly dy over dt is equal to d by dt of 3t minus t cube. So here again the derivative of t with respect to t is 1, and the derivative of t cube is 3t square, right? So here we have used this result, that is the power rule, that is the derivative of t raised to n with respect to t is n times t raised to n minus 1. So here we have 3 minus 3t square, and taking 3 common, we have 1 minus t square. So now first we'll find the dy over dx. So dy over dx is dy over dt divided by dx over dt. Now see, dy over dt is 3 times 1 minus t square, and dx over dt is 2 times 1 minus t. Now here we have 1 minus t square, and it can be factorized as 1 minus t and 1 plus t by making use of the identity a square minus b square, that is a minus b, a plus b, and here we have 2 times 1 minus t. Now this common factor get cancelled, so we are left with dy over dx is equal to 3 times 1 plus t over 2, right? And we have to find the derivative at t is equal to minus 2. So dy over dx at t is equal to minus 2 is given by 3 times 1 minus 2 by taking t is equal to minus 2, and here we have 3 by 2 times minus 1, that is minus 3 by 2, right? So the slope of the tangent to this curve y is equal to f of x at this point t is equal to minus 2 is given by minus 3 over 2. Now let us find out the second derivative of y with respect to x. So now the second derivative, that is d2y over dx2, is given by d by dx of dy over dx. So now let us substitute dy over dx as this quantity. So we have d by dx of 3 by 2, and here we have 1 plus t. Right now 3 by 2 is a constant, so we have 3 by 2, then we have d by dx of 1 plus t, right? So we have 3 by 2. Now see, the derivative of 1 with respect to x is 0, being a constant. So we have simply here dt over dx. So the second derivative, that is d2y over dx2, is equal to 3 by 2 times dt over dx. So now from this expression, we see that dx over dt is equal to 2 times 1 minus t. So if we take the reciprocal, then we have dt over dx as 1 over 2 times 1 minus t. So we can now substitute dt over dx equal to 1 over 2 times 1 minus t over here. So we have 3 by 2 times 1 over 2 and 1 minus t. So this is 3 by 4, and here we have 1 minus t. So the second derivative, that is d2y over dx2, is 3 over 4 times 1 minus t, right? And we have to find the second derivative at t is equal to minus 2. So substituting t is equal to minus 2 in this expression, we have 3 over 4, and here we have 1 minus minus 2, right? So this is 3 over 4, and here we have 1 plus 2 minus minus plus, and here we have 3 over 4 times 1 plus 2 is 3. So 3 and 3 get cancelled, so we are left with 1 over 4. So the second derivative at t is equal to minus 2 is equal to 1 over 4. So now consider this problem in which a curve y is equal to f of x is defined by these two equations. X is equal to e raised to t square minus 1. and y is equal to e raised to t cube, and we have to find dy over dx and d2y over dx2, and that is the second derivative. So here first we'll find dx over dt. So x is e raised to t square minus 1. So dx over dt is given by the derivative of e raised to t square minus 1. So now first we'll differentiate e raised to t square minus 1 with respect to t square minus 1, right? And then we'll apply the chain rule. So we can write this notation also. Here we write d over d of t square minus 1, and here we have t square minus 1, and then by chain rule will differentiate t square minus 1 with respect to t. Now the derivative of the exponential function is the exponential function itself. So here we have e raised to t square minus 1, and by chain rule the derivative of t square minus 1 is simply 2t, right? Because here the derivative of t square is 2t and derivative of 1 is 0, being a constant, right? Now let us find out the derivative of y with respect to t. So dy over dt is equal to d by dt of e raised to t cube, and here also we'll make use of the chain rule. So first we'll find the derivative of e raised to t cube with respect to t cube, and then the derivative of t cube with respect to t. So now the derivative of the exponential function is the function itself, that is e raised to t cube, and then the derivative of t cube with respect to t is 3t square. So we have 3t square e raised to t cube, right? Okay. So now the derivative dy over dx is given by dy over dt divided by dx over dt. So dy over dt is 3t square, and here we have e raised to t cube, and dx over dt is given by e raised to t square minus 1, and we have here 2t, right? So now we can simplify this expression. Here this t and this t get cancelled, and we have 3 over 2 and e raised to t cube, and here we have this t raised to 1 because t and t get cancelled, and here 1t remains, and t e raised to t cube minus we can take e raised to t square minus 1 to the numerator. So we have minus t square minus 1. So we have 3 by 2t, and e raised to t cube minus t square plus 1, right? So this is the expression for dy over dx. So now dy over dx is 3 by 2 t e raised to t cube minus t square plus 1. And to get the second derivative, we'll differentiate both sides with respect to x. So d by dx of dy over dx, and we have here 3 by 2 and d by dx of t times e raised to t cube minus t square plus 1, right? And here we can see that we have the product of two functions. So now this is d2y over dx2, and here we have 3 by 2. Now see here we have the function of t, that is t e raised to t cube minus t square plus 1, and here we have to differentiate this function of t with respect to x. So what we will do, we'll here make use of the chain rule. So first we'll differentiate this function with respect to t. So here I will write d by dt of t e raised to t cube minus t square plus 1. And then we differentiate dt, that is t, with respect to x, right? So here what we have done here, to get the second derivative, we have 3 by 2 d by dx of the product of these two functions. Now here we have x. So what we will do, we'll differentiate this function of t with respect to t, and then by chain rule we have dt over dx, right? And from this expression, dx over dt is equal to 2t times e raised to t square minus 1. Dx, that is dt over dx is equal to 1 over 2t e raised to t square minus 1, right? So here I will substitute 1 over 2t times e raised to t square minus 1. So now we have 3 by 2. Here I will use the product rule, that is d by dt of uv. If u and v are functions of t, then we have u, then we have dv over dt, and then we have v and du over dt, right? So we can take the first function u as t and v as the second function, right? So we have t, then the derivative of uh, e raised to t cube minus t square plus 1, and then we have e raised to t cube minus t square plus 1, and the derivative of t with respect to t, and then dt over dx is 1 over 2t, and here we have e raised to t square minus 1. So now d2y over dx2 is equal to 3 by 2, and then we have t. The derivative of e raised to t cube minus t square plus 1 with respect to t cube minus t square plus 1 as the exponential function itself. So we have e raised to t cube minus t square plus 1, and then by chain rule the derivative of t cube minus t square plus 1 is 3t square minus 2t, and then we have here e raised to t cube minus t square plus 1 times the derivative of t with respect to t is 1, and here we have 1 over 2t and e raised to t square minus 1. So now we have to simply reduce this expression into a simple form. So we have 3 by 2. We can take this factor common. So we have e raised to t cube minus t square plus 1, and in the brackets we have t times 3t square minus 2t plus 1, and here we have 1 over 2t e raised to t square minus 1. So now this is 2 times 2 is 4, so we have 3 over 4, and then here we have this factor t, and then we can take this e raised to t square minus 1 to the numerator. So we have e raised to t cube minus t square plus 1 minus t square and plus 1, right? So taking e raised to t square minus 1 to the numerator, and here we have 3t cube minus 2t square plus 1, right? Okay, so now we have 3 over 4t, and e raised to here we can see that we have e raised to t cube minus t square is minus 2t square, and 1 plus 1 is 2, right? And in the brackets we have 3t cube minus 2t square plus 1. So the required expression for the second derivative of y with respect to x is given by this expression.